In this lesson, we have the basics for what will become electric motors. In other words, it is this fundamental phenomenon, this rotation of our coil, which is a rectangular coil that I have shown here, the rectangular coil that is going to end up rotating in this external magnetic field that we have set up between the North Pole and the South Pole of the magnet. And for this discussion, we're not going to worry about mechanically how is it possible to get current to run in this rectangular coil and have an axle that can rotate. So mechanically, how is that possible? We won't talk about, brushes and motors and how it's possible to let the electricity flow and still rotate, but just take for granted that it is possible. Now, please do not put in the green end vector or the shade in the rectangle quite yet. The biggest challenge I think we have in terms of understanding what's presented in textbooks and notes on the rotation of the coil really is perspective. You have so much three-dimensional motion occurring, and we are translating it into two-dimensional images, as you'll see in a moment, that not getting lost in the perspective is very important. So let's take a look at what we have here. So we're going to start with side 1, and we are going to identify the current. So we have the current I in side 1, right, traveling in this direction. We have the B field going from north to south here. So when we do IL cross B, we get a magnetic force on side 1 pointing straight up. Okay, well, let's look at side 2. Side 2 has the current running now to the right parallel to B. Well, that is important because what we get for side 2 in this orientation, when the coil is lying flat to the B field, we're taking that as our initial orientation, we have that the current through the second portion is now parallel to the B field, so we get sine of 0 degrees when we do IL cross B. So we get no magnetic force in section 2, and let's jump over here to section 4. So in section 4, we have the same thing. I4 is parallel to B, so FB equals 0 in section 4. Well, that only leaves us with section 3. In section 3, we're going to do the same thing. We have the current through section 3 running in this direction. We have the magnetic field going from north to south. When we do IL cross B, we get thumb down. So there we have our rotations, our force and our torque and our rotations, and that's the rotation I have showing here. So this coil is going to want to rotate in a clockwise sense as seen from this Roman numeral 3 perspective. All right, we'll get to the green A vector in a moment, so please still leave that off your notes for the moment. Well, the perspective that's often shown in textbooks is the perspective I have here in the middle of the page. So this perspective that I have shown here is what the person that was standing behind the North Pole of the magnet would see. So this person, the view from Roman numeral 1, sees this. What they see is the rotation of the coil has occurred, and now the coil is standing upright. Sees this when the coil has rotated. Let me add that in here. When coil rotates up 90 degrees. All right, so I1, section 1 we just talked about. FB is going to pull it up. FB here is going to pull down, so it's going to rotate, and this perspective in the middle of the page is when the coil is at the very top. Now, when the coil is at the very top, what we have is a situation where there will be no torque generated, no rotation in this position. So we will get no rotation in this position, and add the word only. So this is the only time you have no rotation. So if it's perfectly up at 90 degrees when we do our IL cross B, right? Our B's are into the paper. In every case, the I's are now going in these directions. So comes down to the left and up. And when we do our right-hand rule, we get all of these forces which cancel out perfectly. They're just pulling apart. So there's stress on the coil, but no rotation. Now, we are going to use this green vector N in our next page of notes, so please put it, now we're going to put it in. We have had the area vector before, way back from Gauss's law, and we're going to introduce the area vector again because we're going to see it becomes useful. The area vector in the rotating coils for magnetism is given as perpendicular to the area of the coil, so it'll be, again, normal vector, perpendicular. Green back in here, perpendicular, and the direction is given by taking your right hand, spinning your fingers in the direction of the current, and sticking your thumb out. So the n hat vector, spin fingers in direction of the current, so spin, right hand, fingers in direction of I, curl to make fist, and stick your thumb up. And there you have it. That's the n hat direction. And that's by convention. And that will become very important in our next page of notes, where we're going to actually track the rotation of the n hat vector. Because notice what happened in going from our initial position to our rotated by 90 degree position was the n hat vector actually rotated from straight up to being aligned with the B field. So that is going to become very important in our next page of notes. And I have typed in down here, I guess we don't really need to write in everything in green that I put in because it tells you again down here, but if you wrote it in, that certainly is not going to hurt you. It emphasizes what you need to do for your n hat vector.